Okay. So, on one side of the multiplexer, you have got what is called your data lines. Yeah, you have what is called your data lines, and on the other side you have got your output line. Okay, so on one side you have your data lines, on the other side you have your output lines. Okay. All right. Now I just want to show you what that would look like. There we go. Okay. Right. Now, the right hand side is what it looks like, all right? And the left hand side is what you're supposed to think of it, how it works, the mechanism, all right? Except for the left hand side, they missed out 2 lines, all right? Okay, so let's have a look at it. Let's have a look at the right hand side first. Let me try and zoom in this thing. Usually in these windows, what is the proper zooming? Oh, here, all right. Okay, so have a look at this. There's the data lines, D0, D1, D2, D3, yeah? Okay, that's the data. There's the output line, only one output, F. And then there's the selector lines or controller lines. Selector lines or the controller lines, all right? So what do the selector lines or the controller lines do? Well, basically, they do the connection which data will be connected to the output line, which data line will connect to the output line, yeah? All right, so now, have a look at this picture. Left hand side is data, that's already provided, right? Data will already be provided. Selector is the controller, that's you or your design, which will select which data line to choose, right? It's choosing which line. And your output is, whatever the choice is, it's going to connect to that. Now, this is how it works. Obviously, there's some thing, but this is the way to think of it. So, on the left, you've got your data line. The selector lines are missing. Data selector switch is missing. And basically, all it's doing is only allowing one output. Only one output gets selected, right? Only one output gets selected to be thrown onto the output line. So can you see the switch? It's like a lever switch. At one point in time, only one data from the left hand side will get a chance to go onto the output side, right? And which data will it be? It's according to your selector line. According to your selector line. All right, now let's zoom into that. Everyone got a fair idea of what's happening here? All right, now let me show you. Let's start off with a slightly more difficult case. Okay, we try and zoom into this. How the hell do you zoom in? All right, can you see there are 4 data lines, D0, D1, D2, D3. Those 4 data, it's coming from somewhere. It may be 4 different sensors, right? 4 different sensors, right? And the selector over here is selector 0, selector 1, right? 2 selector lines. And there's only one output line. Let me give you an example, something which you may be familiar with instead of explaining it in terms of abstract chip. Now, there's a security, you are a security guard, right? And you're sitting at the security desk. You've got one screen, one computer screen, right? Okay, one computer screen. Now, but there are 4 cameras. 4 cameras. Camera 1, camera 2, camera 3, camera 4. Yeah? Okay, camera 4. 4 cameras. So there should be 4 video feeds. You want 4 security cameras. But there's only one screen. You only got one screen, right? Now, if you want to select camera number 1, we in our digital side we say camera 0, camera 1, camera 2, camera 3. If you want to select camera 0, you type in the code 00. The moment you type 00, 00 in binary converts to what in decimal? It's 0. So camera 0, the output will come online, will be shown. Then if somebody says, hey, I want to see camera 3, what's happening in zone 3? Let's look at camera 3. So straight away 3 is what? 1, 1. Type 1, 1. Right? And then camera 3 will be shown. Because you've only got one output. Only one output, but 4 inputs. There are many inputs, but only one output. And you want to see all of them. At some point in time, you want to check this. You want to check camera 2. So you type 1, 0. Then you are the video signal from camera 2 comes onto the screen. Have you guys seen this probably in movies or maybe in real life where they have a security control center and they want to check in, oh, check camera 3. And then straight away somebody does something on the computer, camera 3 comes onto the screen. Okay, let's see what's happening in camera 4. So straight away camera 4 comes. This happens in a lot of Hollywood movies and TV series and so forth. You've probably seen this, right? Not in real life, but probably seen it in the movies, right? That's using a multiplexer. In fact, if you ever get, some of our students did do some of their industrial work experience in security companies. And in fact, the actual term, if you look in the advertisements on paper, they actually say video multiplexer. The actual equipment is called a video multiplexer. The concept is the same. The basic fundamentals is the same. You know, you might see, anybody did the work in, okay, you guys are second year, you'll do it at the end of this year. Some students did their attachment with security companies, not as security guard, but as the technical guy, right? Camera installation and all that. Okay. Yeah. So, yeah, you need to know how to connect your 16 cameras to your video multiplexer, and you've only got one screen. So you want to just see one screen at a time, right? One camera at a time. So if somebody says, hey, I want to check camera 2, what's happening at camera number 1? So 0, 1, right? 0, 1 is number 1. So the data which is coming from camera number 1 will come onto the screen, right? Now you're probably starting to get a visualization now. So that's how these multiplexers work, guys. Now, obviously, if there are 4 data lines, right? If there are 4 data lines, how many control signals do you need to control 4 data lines? You need 2, right? Because 2 to the power of 2 is 4. What if you had 8 data lines? 8 data lines. How many control lines would you need? You need 3. Right? 3 control lines, because the control lines in binary. The control lines are in binary. Right? You'll need 3 data lines, which you'll then connect to your 8 data inputs coming in. Hey, what if you had a simple case? What if you had the case where you've got only 2 data lines coming in? Only 2 data lines coming in. How many control lines would you need? 1. All right? Okay? So, the names are, how they name it is this. Let's now go back to the basics. Let's see the simple one first. You know when they say 2 by 1, or sometimes they say 2-1. 2 by 1, or sometimes they say 2-1. I think the second number will always remain a 1. Why will it always remain a 1? Because there will only be one output. Always, there's only one. That's the thing about multiplexers. Let me show you the 3 or 4 different types of multiplexers. That's the 2 by 1 or 2:1. The second number will always be 1. Why? There'll only be one output. Let's look at the 4 by 1. There we go, 4 by 1. Only one output. What about over here? 8 by 1. Only one output, right? So from that, you should be able to conclude, hey, if there's 8 outputs, 8 data lines coming in, you need how many control lines? You need 3 control lines. All right. Now let's have a look at the 4. Let's do all of them. And 16. 16, how many data lines, guys? 4. Now, this is the catch here. All right. Sometimes you will be given you require 16 data lines. Let's say there are 16 cameras, right? And you have only a 8x1 multiplexer. Or you have many 8x1 multiplexers, but no 16x1 multiplexers. Because remember, number of data lines has to accommodate, the number of data lines has to be accommodated by the multiplexer, right? So what do? You can build bigger multiplexers using smaller multiplexers. So just note that down in your exercise book. You can build 4x1 using X. I'm going to leave that as a question mark. You guys find that out on the internet. You can build a 4-to-1, I call it 4-1 multiplexer using question mark 2-1 multiplexer. Or you can build 8-1 multiplexer using question mark 2-1 multiplexer. You can build 8-1 multiplexer using question mark or blank space, right, fill in the blanks, 2-1 multiplexer. So what I'm trying to say over here, you can build bigger multiplexers using small multiplexers. And the good news is you can go the other way around as well. You can go the other way around. If you've got an 8-to-1 multiplexer, but you only need, right? Let's do a simple problem over here. Most of our work, guys, is intuition. It's just for you to understand the fundamental concept. Okay, let's say you have this. But hey, and the only thing I've got in the lab is a 4:1, right? 4-to-1 multiplexer. That's the only thing the technician can give you. All right. But you want to build the other way around. You want to build something smaller. You want to build something smaller. How will you do that? You want to build something smaller. You want to build a 2-to-1 using this guy. How are you going to do that? Right now, I want you to absorb this. Take it for a little while. Let me run you through the combinations, right? And we'll come back to this question here. This is a practical question because at most of your life, most of your engineering life, some equipment or some chip may not be available, right? Second year engineering, third year engineering, final year, even in your final workforce, something will not be there and you'll have to improvise or you'll have to rebuild something based on putting two things together, okay? You'll have to build something from scratch or you might have to redo something. I mean redo meaning you have to repurpose something or something along those lines. I remember when I was Robocon instructor so many years ago, we didn't have much good motors. So what we used to do was, like you can't buy good motors, good high speed, high torque motors. High speed, high torque. You guys know what speed is? Torque is how much power, how much tightness with which it rotates the wheels, right? So we couldn't find them in the local market. So what we did is we went and purchased hand drills. You know those hand drills for drilling, the battery pack one, right? We bought those hand drills, we ripped the motor out together with the gearbox, and that was a high-speed, high-torque motor. So you have to start thinking along those lines, all right? Because definitely, already if you haven't faced it this year, you'll face it next year, and you will most likely face it in your final year as well when you're doing your project. There will come a time when what you want is not available, and you have to put it together, right, using something else. All right, so let's do a quick review. My question again stands, and we'll come and discuss this in a short while. There's two questions. How do we upgrade? How do we use smaller multiplexers and make bigger multiplexers? Or the other way around, second question is, how do you use bigger multiplexers to make a smaller multiplexer? So how do you use 8-1 or 4-1 to build a 2-1, right, something downgrading? Or how do we use many 2-1s to upgrade, to make an 8-1 or to make a 4-1? All right, so we'll come back to that question shortly. All right, now. Okay, guys, let's now have a look at this. Okay, this is a 2-1 multiplexer. There's D0 and D1. There's two data lines. Obviously, 2 data lines, 1 input signal, right? 2 data lines, 1 input signal. Your output is F, only 1 output. Multiplexers, only 1 output. There's something else known as decoders, which we're going to do in the next half an hour. That's a separate story, right? Multiplexers, only 1 output, many data lines, selector lines. Okay, so there's three things over here. Usually, for most other situations, you have input, you have output. In this case, you have data, you have selector inputs, and you have only 1 output. So 1 output, 2 data lines, right? The data lines determines, the number of data lines determines the number of selectors. So if there's 2 data lines, there'll only be 1 selector. So if S is equal to 0, right, that switch, remember the switch? If F is equal to 0, sorry, S means selector. If S is equal to 0, this thing here points to input 0, all right? If S is equal to 1, your output will equal to 1. Set, all right? How did it will equal to, not equal to 1, will be connected to data 1. Maybe you supplied a 0 in data 1, so your output will be 0. If you supplied 1 to data 1, your output will be 1. Whatever data, whatever line is there, whatever the camera is looking at, whatever the camera is visualizing, that's exactly what the security man will see on his screen. All right? Okay? So the data is coming from the camera. So those 2 lines may be connected to some cameras or some sensors or whatever it is. All right? Okay. Now, let's look at the next one. Now, guys, one of the questions we may ask you is, hey, that's a block diagram, but what's sitting inside it? How did we build this little thing called multiplexer? Right? How did something known as a multiplexer get built? Well, what would be your truth table? What would your truth table look like? Well, on your truth table, you'll have data 0, data 1, and selector on the input side, and on your output side, you'll have F. Okay. Let's have a look at the truth table. Data 0, data 1, and selector, and your output is F. Guys, this is on the Moodle shell, right? But make sure you guys understand this. So the circuit is simple. So if somebody gives you a multiplexer and says, hey, I've got a 8:1 multiplexer, can you draw what is inside that block? And it's all basic, again, basic theory, what you've been doing in the first 7 weeks. So if we give you a block and we describe to you what the behavior is, from that behavior, you should be able to draw your truth table. So remember, you had 2 inputs, you know, 0, 0, 0, 1, 1, 0, 1, 1. But the third input was your selector line. Your third input was your selector line. And you already know what your output is, right? Okay? So this is how you went about populating it. Now remember, if you look at the block diagram, you say, hey, but we were not told what our D0 and D1 is. Well, simply because there's 2 inputs, you can populate it, right? You can populate it. So this, in fact, it becomes 3 inputs. Your data is your data input. Your selector is your selector input. So there's 2 sets of inputs, 1 output. And this is what your equation look like. Your F is equal to D0 S bar or D1 S. Okay. Now, if you want to think of this as, right, basically you can say, okay, we can, if you want to use your back to basics method, you can always go back to basics and design your system like this. Basically, what are we doing over here, guys? Sorry. What are we doing here? we are trying to find what's going to sit inside that block using our basic method, right? And over here, what they are doing is saying, hey, the circuit is so simple, we can predict what it will be, right? We can pretty much read into the circuit, into the block diagram, because there's only 3 inputs, 1 output, right? And the output is equal to D naught when S is equal to 0, and equal to D1 when S is equal to 1. So you can pretty much find out what those equations are. Right, let's have a look at this. Let's look at the next one. If S0 and S1 are 0, 0, right? S0 and S1 are 0, 0, your data 0 will connect to your output F. What that means is that your output F, whatever data is sitting on data 0, will then equal to output F. Yeah? Okay. If your S0 and S1 are 1, 0, 0, 1, right? S0 is 1 and yeah, S1 is 0, 0, 1, then your data 1 will connect to your line F. F is output function. F is function, right? Similarly, if you have a 1, 0, right? Okay, you have D2. And if you have a 1, 1, D3 will come into output. So can you see 2 sets of input? Firstly, it's the data lines. Secondly, it's the selector lines. And then only 1 output. All right? Okay. Guys, I'm going to give you a chance over here. Or maybe it's going to take too much. It's how many inputs altogether in this case, guys? How many inputs? 16. Sorry, 6 inputs. So how many possible combinations on your truth table? Come on, guys. 6 inputs. 4 data lines, 2 selector lines. So how many possible combinations will that be? 2 to the power of 6, right? 2 to the power of 4 is what? 16. 2 to the power of 5 is 32. 2 to the power of 6 is 64. So if you were to draw, this is where it comes in. If you were to draw this using a truth table, your truth table will end up with 64 lines, right? Okay, so if we go back to basics, it becomes very, very hard. But you can still do it. You can draw a 64-line truth table. From that, you will get your sum of min terms. From your sum of min terms, you can then go and, from your sum of min terms, you can then put together your Carnot map, and you can draw what your function f will look like. All right? But we just went ahead and instead of doing 64 lines, you just use intuition. All right? There are 6 inputs, D3, D2, D1, D0, S1 is 0. Remember, we go from most significant bit to the least significant bit, right? And 1 output. Therefore, it is difficult time to use K-maps. A 64 input K-map, how are you going to draw that? Right? That's going to be, that's probably going to be a 4x4. 4 4x4s. There will be 4 4x4 Carnot maps, right? Stacked on top of each other. Do you remember one of our last lectures, I think the last lecture, which we had in week 7 over here in this lecture room, we talked about a 5-variable Carnot map and a 6-variable Carnot map, right? 6-variable Carnot map, you'll need 4 layers of 4x4 Carnot maps, 4 layers, right? Okay, now, so that's too hard. So what is a more easier way to do it? Remember, at any one point in time, only one input gets selected. Only one input gets selected, all right? So we can say, okay, if f is equal to d naught when s is equal to 0 and s1 is equal to 0, s0 is equal to 0. So using our concept which we've already learned, by from our earlier studies when we were doing sum of products, right? We can then very quickly deduce these functions. So let me put this into a truth table, right? Not the 64 truth table, but another way to draw the truth table is Okay? Now, let's now look at this. When both is 0, 0, 0, 0, 1, 1, 0, 1, 1. When both is 0, what do we get? Our output is equal to D0, D1, D2, D3. That's one way of visualizing this. All right? Even though implicitly we have over here behind the scene we have D0, D1, D3 sitting part of the table as well on the input side. Right? But our outputs, we know whatever is in D0 will equal here. Now, let's now flip back to the note now. Now from that, what we learn is that F is equal to D0, S bar, S1 bar, S0 bar, and so forth. Those 4 lines. Right? Now, what I'm trying to project over here is this. We can do it using our first 7 weeks, you know, like truth table, Kano maps, but it becomes very difficult. Right? It can become very, very difficult because there's so many lines for you to handle. I think even your exercise book, 1 page is only about 45 or 50 lines. So you'll need 2 pages, 2 sheets of truth table, right? And then your Kano map will be a 4x4 stack. So 4 layers of a 4x4 Kano map. So this is the fastest way to determine it because the system was so easy. The system was so simple. Based on the fact that your particular thing, your particular output is only D0, D1, D2, and D3. All right, now, so that's your function. That's your formula for function F. Remember, in a 2x2, in a 2:1 Kano map, multiplexer, we were able to find what our F was. Very simple, right? And then from there, we said, hey, we can do the same using this method here because it's so simple. Now, let's talk about our 8:1. Let's talk about our 8:1. So again, you've got your inputs, 3 selector lines this time, 8 data lines, 3 selector lines, 1 output. So therefore, how many total inputs altogether? 8 plus 3 equals 11 inputs. If you were to draw the truth table, how many lines will there be on your truth table? 2 to the power of 11, which is what? Can somebody give me what is 2 to the power of 11? 2048 lines of truth table, right? So what I'm trying to say here, if we go our traditional method and do the truth table, we're going to end up with 2048 lines on our truth table. That's just too much. It won't be feasible. Even if you were to do it in your exercise book, I don't think it will fit your exercise book, right? Okay, 2000 lines, because 1 page is 50 lines. Yeah, maybe 40 pages, you should be able to do it, 40, 45 pages, right? But then you have to track what line is happening where. It's too difficult. So that's why we have to resort to this method, right? And how did we come up with this method? This method, we saw the pattern. We saw the pattern over here when we did the 2:1. When you do the 2:1, it was easy because only 3 inputs, 8 lines, right? We saw that A, and then we were able to pick up what's happening here, right? So it's only that particular line will go on when that particular input is selecting it. Okay, so then we learn from this. Okay, all right. So that's our function for our particular 8:1. All right, now, is there a 16:1? Yes, there is. Not in our notes, but in reality, there is something known as a 16:1. Okay. Right, guys, I'm going to pause over here, and I want you to look at this example. But before that example, let's consider the case of this guy here. All right? Now, let's remember I said we did a quiz question, I said. A question to you guys. What if we are given this, but we only require we want to build a 2:1 multiplexer. 2:1 multiplexer. But the technician only had 4:1, 4-1. Right? And you need, and you've been given a 4x1, and you need a 2x1. What are you going to do? How are you going to handle this? Discuss with your neighbor. What are you going to do? Look at the truth table you want, you can draw the truth table. How can we transform? So if you want, you can write this question down, it might come in your final exam. How can we transform our particular 4x1 Carnot map, not Carnot map, 4x1 mux. Oh, the nickname for a multiplexer is mux. Okay. How can we convert our 4x1 mux into a 2x1? What do we do? It's a simple thing which you can do. It's something similar to earlier on. You may have, there were some notes there on how we convert our 3-input NAND gate into a 2-input NAND gate and so forth. Something very, very similar. Right? And let us say your data, you can choose which lines is your data lines. You can choose which lines, right? All we are asking you, how do we downgrade this big multiplexer into a smaller multiplexer? How do we do this? Right. Anyone got a solution? Anyone? Throw an idea. Right? And your inputs coming in will be only 2 inputs. Your 2 data, sorry. Data coming in only 2 lines of data. Because that's all you need. But you want to silence some of the lines here. You want to kill some of the lines. What are we going to do? Anyone got an idea? Okay, so how do we downgrade? Basically what you can do, guys, is if you look at the truth table, it's to play with the selector line. We are playing with the selector line here. If you look at the truth table, if our S0 is 0, right? S0 is 0, definitely, sorry, if S1 remains 0, if S1 becomes 1, that means definitely what? If S1 becomes 1, it's either data line 2 or data line 3, yeah, in use. And if S1 is 0, the only possibilities is data line 0 and data line 1. So all you got to do is ground data line 1, selector line 1. Ground selector line number 1. Okay? Ground selector line number 1. That's it. That's your answer. So if you provide a 0 to S1, there's only one switch then. Only one selector switch left. And that's going to play with, that's going to only allow data line 0 and data line 1 to connect to your F. Okay, data line 0 and data line 1 to connect to your F. Data line 2 and 3, no problem. It's going to be just drop out. It will be useless. No matter what data, or it will become don't care. It will become don't care. No matter what data you feed into it, it will never get a chance to make it to line output F. Okay? All right. Now similarly, if somebody asks you to downgrade this one here so that it can only handle 4 lines of data. So you want to downgrade this 8-1 multiplexer so that it should only handle 4 lines of data. So what you will do is just take selector line 2, the most significant selector, and make it 0. Make it permanently 0. Permanently feed a 0 into selector line 2. And then only data line 0, 1, 2, and 3 will be considered as possible outputs for line number F. Okay? Alright? All the others will just disappear. Line 4, 5, 6, 7 will become don't care. No matter what data you feed into it, it will never get a chance to go into F because selector line 2 has been made grounded. Because if you look at the chart over there, what's written over there, in order for data line 4, 5, 6 and 7 to make it into F, your selector 2 has got to be a 1, right? So what we've done is we switch it off permanently. All right. Okay. Let's take a chance and take a few minutes and see the application of this, guys. What is the application? Okay. Now, if you get a chance, guys, there was a 20-mark question on multiplexers in last year's final exam paper. Have a look at that, all right? A lot of students, I think almost all the students got that wrong, all right? So have a look at that. This is a simple question. We have a function of ABC, sum of minterms, 0, 1, 2, and 5, and we want to use a multiplexer to build it. This is the application. You may be going, hey, apart from that video idea, the security guard idea and all this, and sensors idea, where else can we use it? Well, we can use it in this particular situation. You see, if we were to build this using AND/OR systems or NAND, you might end up with a few AND gates and a few OR gates, one OR gate and a few AND gates. We can build it with one chip over here, just one chip, and that's the multiplexer chip. The multiplexer chip has already got the AND/OR system sitting inside it, right? So you can build it using one chip, and that's how you do it. You see, the data lines are already fed in, right? The data lines are already provided. You don't choose the data lines. The selector lines are ABC, and that's how you reflect that. Have a look at the second system. So these are two examples. I want you to just note in your exercise book. I want you to note in your exercise book to please, what page number would this be? Page 7. Okay, please take note of page 7. All right. Now, so the first example is we are trying to use a sum of minterms, right? We've got a sum of minterms and we want to use a multiplexer, a mux, 8:1 mux to develop or design or implement that sum of minterms. And all you need is one mux. You don't need, that's the good news, you don't need any of the other, you don't need any of these other AND gates and OR gates and NOT gates and so forth. Just one chip will take care of it. Okay? So it's very simple to, system design is very simple using a mux. Now let's have a look at the second example. The second example. I want you to take note of this, okay? And we'll come and do it in the next next particular lecture as well. In the meantime, I'm going to just quickly go to the decoder part. There's something known as a demux. We'll have a look at that next on Wednesday. I want to show you a decoder. All right. This is another device. So there are 4 devices which we will be learning out. We'll be learning about multiplexer. The opposite of multiplexer is demultiplexer. Multiplexer we've completed. The opposite of multiplexer is demultiplexer. Then there's another family, another cousin, but it's not the same thing, known as decoder. And the opposite of decoder is encoder. So 2 families. One family is the mux and demux, the opposites, like male and female. And then there's encoder and decoder. All right, let's talk about our decoder over here. In our decoder, very similar concept to the mux, but not exactly the same thing. In our mux, there was only one output line. Only one output line. So at any one point in time, only one piece of data got selected. Now, in our decoder, it's the other way around, slightly different. There is no selector lines. There's no data lines, sorry. There is no data lines. There are no data lines, no more data. No data handling, no security camera. In this case here, it's more like turning on security lights, right? You've got 2 inputs, 2 control inputs, and at any one point in time, you only want to turn on one device, right? Okay, you only want to turn on one device. Okay? So, if you've got 2 input lines, 4 output lines. If your A0 is 0 and A1 is 0, so you've got 0, 0, your output 0 will become a 1. your output 0 will be a high. But all the other outputs, they'll be a low. So once again, for decoder, at any point in time, only one of the outputs will turn on, right? So let me give you a practical example. Let's again look at a practical example. Let us say you have traffic lights. Let's say there's 4. Let's say in Fiji there's 4 traffic lights. You've got green, orange, red, and blue. All right? Blue means accelerate. Okay? Green means go, red means stop, and orange means slow down, blue means accelerate. Okay. So at any one point in time, you can only turn on one light. You can't obviously turn on red and blue at the same time. Only one is allowed to be on at one point in time. Now, a basic first year student, if you tell them, hey, I want you to build a circuit, what they'll do is, they'll make 4 switches, 1, 2, 3, 4 switches. Each light, right, they'll have 4 switches. Okay? Okay. They'll have 4 switches, right? And they'll say, okay, which one do you want on? And let's say it was that type of controller where a human being is controlling the traffic light. So at any point in time, he's switching on one and turn all the others off. Somebody says, okay, it's green now. Then he turns on green, right? Okay, and turns off the other one. Okay, now it's orange. So it turns on orange, turns off green, right? Or turns off green and then same time switches orange on. Then somebody says, okay, now we go to red now. So he switches off orange, turns on red, right? Then from red he goes back to green. Green, then let's say blue, right? So at any point in time only one can be on, right? Now in the first case, if you were using some basic electronics knowledge, you'll have 4 switches, right? But if you use a decoder, you end up with only 2 switches, only 2 control lines to handle them all right? Okay, so this is how you'll do it. If your A0 is A0, A1 combination is 0, 0, output 0 will turn on. If your input combination is 0, 1, output 1 will turn on, all the others will off. If your combination is 1, 1, output 3 will turn on and all the others will turn off. So at one point in time, only one is on. Only one. Okay? And what was in multiplexer? There was only one output. And it was the data which was being selected. Over here, it is the which line to turn on. So even if, let's say, you've got 4 fans, or I don't know, if you've got 4 motors to turn on at different times, right? Same thing. Same thing. All right? And these two circuitry is used in many industrial applications. Like I told you, in terms of, in fact, when you look at the traffic lights is not based on 3 lights. There's actually more. Look at it. One circuit, because remember, let's say consider the McDonald's junction over here on Grantham Road. It's actually 3 lights. Then there's some arrows over there. There's some, what do you call the man walking, and the man has to, don't cross and cross. Then there's lights on that side, Grantham Road side. There's lights on this side from coming up the hill. There's lights from down here. So if you see it, it actually turns out to be a large group of lights. And they use encoders as well as multiplexers, right? They do a number of things over there. So this is what we are working towards. We are working towards giving you enough tools so that if somebody says in your thing, hey, I want you to use, they'll say, hey, our computer system is broken down. Can you design our traffic light system using multiplexers and decoders? You say, yes, we can do it. Right? We know how to design that. All right? So this is what is working at. All right, let me show you one more before we finish off for this afternoon, and we'll see you on the other day. Hey guys, if you have a bubble there, that means the output becomes inverted. If there's a bubble there, what does that mean? It's the other way around. That means turn off only one of the outputs at one time, right? All the others remain on. Can you see the bubble in this case? Right? You can do things like that. You can flip things over. Bubble is just a NOT gate. And of course, guys, you can have your, you can do your circuitry using your truth table. 2 inputs only. 2 inputs, how many combinations? There will be 4 possible combinations. But how many outputs? How many outputs? 4 outputs. 4 outputs. All right? Okay? All right. Now, let's have a look at this decoder. You have 3 inputs. But how many outputs? 8 outputs. Now, what does the bubble say? What does the bubble mean? The bubble means that at one point in time, only one output will be off. All the other outputs will be on. Right? Because the initial theory is that only one output will be on, and all the others will be off. But if you put a bubble on, if you put a NOT gate on each line, obviously everything's going to flip over. Yeah? All right? So if you have 0, 0, 0, line 0 will be off, everything on. If you want to turn off, let's say, line 7, it will be 1, 1. If you want to turn off, let's say, line 1, output 1, it will be 0, 0, 1. Right? The concept is very simple. What you've got to think of is this. Okay, there's no switch in this case, yeah. Now, once again, there's some basic knowledge I want to give to you, is that you can build a smaller decoder, you can build a larger decoder using smaller decoders, right? So you can go and type this. Oh, by the way, one more thing I wanted to mention. The naming convention, guys, the naming convention. The naming convention. Can you see over here, the naming is to 1. With multiplexer, with mux, always the name is to have 1 in the end. The second digit is always 1. Why? Because only one output. Now with decoder, it's always input dash output, right? So 3 dash 8, 3 by 8. 3 inputs, 8 outputs, right? 3 inputs, 8 outputs, okay? And in mux, it was selector lines, eh? I mean, data lines is to output, right? So 16 dash 1. Okay, guys, that's it for today's lecture. We'll see you in your next lecture. These decoders and encoders, they'll be used in your lab this week, all right? So please study and revise on lab. Have a look at a few YouTube videos, and we'll be assessing your lab in-house this week, all right? Okay, that's it. Thank you. Guys, your short test results, I'm going to make arrangements so that it can be picked up from one of the lab sessions, most likely Wednesday, 5 to 8. All right? Okay, thank you.